Calc 2, which is what 152 is, its basic theme is integration, also called antiderivative. Now, right at the end of Calc 1, you found antiderivatives of functions. Basically, it's working backwards. Instead of differentiating something and getting an answer, you kind of said, okay, if that was the answer, what would be the original function that would generate it? That's kind of what antiderivatives do. And chapter 152, Calculus 2, basically deals with, at the beginning, a physical problem. How do you estimate the area under the curve? The analogy would be, can you remember Calc 1, where we did what was called the tangent line problem? You basically numerically try to estimate the slope of a tangent line to a curve at a point. And from that place, calculus, in particular, differentiation started. Well, we're going to find the area under a curve, or at least an estimate from it. And actually from that problem, integration essentially starts. We won't do anywhere near as much work as we did in Calc 1. So if I am really good and quick, I will, if you hold on a second, I am going to mute everybody because I'm getting some weird feedback. Yeah, that should work. So what was I saying there? Yeah, I forgot what I was saying there. Yeah, easy to distract me, isn't it? So we won't spend nearly as much time. My goal is to try and get the section 5177 kind of deal as close to being done as possible today. And definitely it will be finished by Thursday when I see you. Because after that point, we stop doing all the numerical stuff and we get into the real good stuff, right? The algebra, the process of finding integrals. And from that point onwards, what the course basically boils down is, how do you find integrals of functions? And just like how do you differentiate, you had product rule, quotient rule, chain rule, all that kind of stuff. Well, when we do integration, you're going to have techniques for finding integrals. And they're going to be things like the power rule, U subs, integration by parts, trig substitution, and so on. And so that will be what we'll spend a lot of time on, getting good at that. And then the third part, just like in Calc 1 was, once you know how to differentiate, wasn't there a lot of, now what can you do with derivatives? And you can do things like find velocities and accelerations and slopes of tangent lines and where the top of hills and valleys are and so on. Well, in Calc 2, once you've found out how to integrate things, what we then spend our time on is, and what can you do with these things called integrals? And you're going to find out that you can find area under curves and between curves and volumes of rotated shapes and work done and surface area and arc length and a whole load of cool things like that. And that's what Calc 2 is about. That's the big picture. We'll do some numerical estimating areas under curves, which is pretty boring, to be honest. Got to be done, but it's something I don't have great excitement about doing, but it has to be done. And then we do the cool stuff, which is the algebra of integration. And then we do the, let's use it to find things. Any questions so far? Right, kind of like a big picture. Right, I'm now going to move over and show you what your Canvas site should look like, and hopefully you've all had you've already been there, but you may have just joined, you know, in the last day or so and not had a chance. Right, this is essentially what your, oops, there. That's what your Canvas site should look like, and here are all the kind of cool things. This one is basically going to be up for the first week really. The fact that you already know how to take this class, you might have figured out how to do the Zoom thing, right? Hopefully you've joined WebAssign, but here is the information about how to do that. And we'll talk later about WebAssign, because that's essentially where all the homework and tests and everything live. There's going to be an office hour. The office hour is 10 o'clock. That might not suit you. So here's a different kind of opportunity if you need to see me about homework or so on. If you come early, because I typically start about 15 minutes before the class, you can ask your question then. Or you can wait until the class is finished and we can answer your question at that side, right? So either side. That's probably going to suit your schedule better, right? Rather than, but feel free, you can turn up at 10 o'clock. It'll be an open office thing. So what will happen is that you'll just have to wait in a queue, just like you might turn up at my physical office and there's somebody there. You wait till they come out and then you go in, right? So you just wait, right? And I'll do it in the top to bottom thing. What else do we have here? Right, well, if I click on this, here is the link, that's that guy there, that you used to get here. I also sent out an email with it. What we're going to have here is the recordings to these Zoom lectures. So when this lecture's finished, probably sometime tomorrow, you'll be able to pick it up here and you click on it, you can watch this video. That's what I'm doing right now, recording. And then Thursdays will be here. And then week 2, 3, all the way to the end, right, will be here. So this particular link in Canvas is where you will find the link to every Zoom lesson, how you get to Zoom, and a recording of the previous ones. If I then go back, hopefully that's the quickest way of doing it. Let's click on this and we'll show you how this course is organized. If you've had me before, this is pretty much what you'd expect from me. We break things into 2-week chunks. Section 5.1 to 5.5, basically chapter 5 with this funny little guy called 7.7, is going to be done in the first 2 weeks. And all the homework assignments, which are all on WebAssign, need to be done by midnight on Sunday the 17th. Do not wait to Saturday the 16th and try and do them. Not a good way. As we go through stuff, I suggest strongly that you go into WebAssign. For instance, today, when it's finished, you should be able to do 5.1 for sure. And probably 7.7. 7.7 is tiny. There are only 4 questions in it. But they're laboriously long to do. It's not hard to do, they just take a long time. And off we go. 5.2 is the beginnings of how to find integrals algebraically. And then some practice at finding them. And then week 3 and 4, we do chapter 6, which is things you can do with integrals. Week 5 has got the rest of integration. I'm going to check that out because that looks slightly out of sync, but that's fine. The only exam, because there are no tests for this class, is that there's a midterm. And that midterm is going to happen round about there. Tuesday the 9th. And it's going to take place from 5 till 8. And it will be covering all of 5 and 6 and whatever bits of 7 I decide to put in. And then we go and we do 2 more weeks, which is the big chapter 8, 2 more weeks, which is chapter 9, and then we do a final exam. So 2 weeks is your kind of normal go-to guy, normally at least, except for this one. Right? That's that. How will you get any questions so far? Right. Now, if I move on, you can see there's help with homework 5.1 and video lectures. So chapter 5, if you click on this, you will find that I have got videos on the topics that we're covering in, say, 5.1, and here's 7.7. And these are videos that, that one there is done by me. It shows you how you can use your calculator to speed up your calculations if you want to use that. Here's how to find areas which represent distances. That's these 3 videos, and you just watch them. Oops, too quick for my own good there. If you scroll down to the bottom, I have got PowerPoint file, so you can watch PowerPoints on the topics. Just a resource for you. If you go above that one and you click on PDFs, here is a number of different PDFs on how to use your TI-84 calculator. And this one here is a PDF that I put together on how to use Sigma, and then later on how to calculate areas under curves. So these are really just, for instance, although you can't see it that well, maybe make it a little bit bigger. Here is an example of how you can calculate distance, and it's just basically a worked example. So I've tried to give you as much resources as I can, because not everyone's the same kind of learner, right? Some of you need to see visually the thing, and others need to write it down, others need to read it, some of you need to hear it. Very often you need a bit of all of them, but one of those is more than the other. So I've tried to give you video lectures, written down stuff, and so on. So you've got lots of different opportunities to see things. Here's a TI emulator. So if you don't have your own TI-84, which can be helpful, here's a little link, and you can download an emulator that is like a TI-84, but it's software. You don't need to worry about that until the midterm. And this little guy here is some graphing software. So if I click on that, you can, hopefully, I think you can do it as y equals, I'll check. There you go. Basically, it's a little, allows you to visualize things, right? So if you want to sketch a function or look at it, Desmos is quite handy. It's probably better than your TI-84 because it's a tiny little screen, and this is nice and colorful, right? So there's another resource for you. Again, any questions, or are we cool? What you need to do, and I'm not going through it because you can all read, is click on syllabus, and it will tell you how to contact me. Will you make sure that you use your college email and not fred@yahoo.com, because sometimes things don't arrive because they get put in my junk mail because, you know, OC filter kills things. Probably the only part I'm going to talk about from this, as I say, you can read it yourself, is how your grade is calculated. So the first thing is 20% of your grade is for turning up in class, participation, right? Being here and taking part. So try not to miss any classes. 30% is going to be from your homework, which is done in WebAssign. Your midterm is going to be 20%, and that's going to be on WebAssign. And your final exam is going to be 30%. And there is some extra credit going around. Right now, the extra credit is for doing, I guess we'll call it Intro to Canvas. If you've already done it, you just shoot me a little certificate PDF, and you've got those points already. So that's a little bit more detail on the kinds of things that you have, and some links to places that might have if you have issues, technical issues or whatever. And e-tutoring, very important. There's a link to that. And out here. Now, this third link called Welcome is provided by the college, and basically they give you lots of help on almost anything you could do it. So there is some computer labs, tutorials on using Canvas. I think they're pretty obvious what they are here. And so you want to look through them. There's tutoring again. And library services and so on. So I've just left that there. You just click on it and it tells you what you need to know. And that's pretty much all I want to say about Canvas. So this is your last chance. Is there anything about Canvas or how your class is going to be organized that you need clarification? Huh. Either, yes.
Will we be able to use notes for the midterm and final exam this course?
Yes.
Awesome.
You are allowed to use, oops. That dog that's barking is the one that's really sick. You wouldn't believe she was sick by the way she barks. Okay. I think she needs some attention. I am going to have a very quick see what the heck she's on wanting. And while I'm doing that, I'll leave you with the WebAssign page. I'll be back shortly. Okay, what's up? So let's good girl. Okay, I didn't keep you too long. My wife's taking over, which was nice of her. Evidently, Bailey needed a poo walk, and Maggie decided to tell me that Bailey needed a poo walk. She's pretty clever that way. Okay, so what you're looking at now is essentially what your WebAssign should look like. Let's click on the first one, this guy here. Come on. Good. Now, all the homeworks are given 100 points regardless of what the number of questions that they have. So they're kind of equally weighted. So as you go through them, you'll get a score, which you can see here. Obviously, I haven't done any. And here are your questions. So what you typically do is you look at the question, you answer it. Basically, you'll do a lot of number crunching on calculators and paper. And then when you're finished, you type in, 15.2, and I know that's wrong, right? And you do 16.5, and I know that's wrong. And then submit answer. Well, okay. And it is wrong, which it just told me. But it does give you some help, and you can do things like watch something, master it, read it. You get 3 shots, and then it's over with. Now, normally, that's not a problem. In this week's work, all this number crunching that I'm talking about, it's typically not that difficult to do. It's just difficult to get the correct answer because it's fiddly. If you're adding and multiplying 20 numbers together, isn't it dead easy to screw up one multiplication or one adding? And when you do that, you'll get the wrong answer, and WebAssign will just say you're wrong. So you just have to be careful, which is not my strong point, right? But that's how you would do it. So if you've never done WebAssign before, this might be a bit of a shock to you, because that's not the usual way that you would do math. Typing answers into boxes, but we still expect you to do the working on paper for your own benefit, because you're going to use notes, as Catherine was asking. And if you've got a good example of a question where the working is written down in a clear fashion, won't that be really helpful if a similar question pops up in the test? Because then you can say, yeah, I remember doing something kind of like that. And then, hey, okay, I can follow my own instructions. If you kind of, you know, if it's kind of hit and miss, then it's not going to be that helpful. And homework, like all homework, is your way of finding out, do you really know what's going on? Because we'll do lessons and you'll nod your head and say, yeah, that makes sense, I can do that. But you don't really know if you can until you've been given 5 or 6 questions. And then you start saying, oh, it's a little bit more tricky when they change that from just x's to x squared. Or if, you know, this is different. And you have to be aware of how you can adapt a technique to take account of the differences, because there's going to be variations on everything. So that's what WebAssign is like. So hopefully everybody here, virtually everybody here, has probably done at least Calc 1. But I don't know if you've done WebAssign, because different Calc professors don't use the same stuff that I do. So this is going to give me my first opportunity to have class participation. So what I want you to do is, do you know that little funny thing that looks like, oh, what's it called now? Reactions. If you have done WebAssign, you'll stick a little thumb up like that. So how many have done WebAssign as in homework? So you see the little guys? So Rena and Sarah and Ariana, I can't see anything from you. So I'm assuming that means that, oh, got one of you. So virtually everybody has done that, right? You've probably then experienced the dreaded, but I got it right, but it didn't like my answer. You ever had a question where you did that? So your cure for that is to send me an email telling me, or doing a screenshot of what you typed. I will look at what the right answer is, and if it's correct, then I just go in and give you the points. Right? I can adjust for that, right? So no biggie, right? So if you've done it and you know you're right, and then, God, I've forgotten because I don't do it. Once you've done it 3 times, does it tell you the right answer, or does it just say hard luck and move on?
Usually tells you the right answer.
Okay, so you should be able to look at your answers, right? Because I'm assuming you had 3 shots that failed and its answer, and say, yeah, that's mine. That is mine. That's the kind of email you send me. Don't send me an email if the right answer is 94 and all your answers were 280s, because you were wrong, right? You were just wrong, right? But if the right answer is 90 and you did 89.9 and 90.1, the chances are you just rounded off slightly different than they did somewhere in the process, because there's a lot of number crunching going on. And that I would certainly fix. You know, I would change it for you. Usual. Any questions before we move on?
Are we allowed more than one attempt on an exam question, or are those all single attempts?
No, the exam, the midterm is going to be quite different from your usual. So since you've asked, I'll tell you right now what it's going to look like. Those who've had me before know, but not everyone's had me before. On the day of, say, your midterm, you won't see on WebAssign your midterm exam until the class starts. So at 5 p.m. and 1 second, it will appear. And you will be given your questions just like a WebAssign homework question. Then you will go through it and you will write all your working down on paper, and you will write the answers into the box, and you get 1 shot and 1 shot only. And you won't get show me another, you won't get help, you won't get anything. Oh, and by the way, now that's came to me, do not use the WebAssign link that says ask your professor for help or whatever it's called, and don't use the link ask for extensions. They never get to me, those darn things, and I don't have the time to go hunting through layers of options till I get them. When you need help from me, you just shoot me an email, right? We just do it good old-fashioned email way, and I can fix it that way. So rewind back again. So the exam starts, you have 3 hours, and then at the end of 3 hours, it locks you out. So that's it over with. You're allowed to keep as many physical notes as you have PDFs, anything that's physically written down or electronically written down is help as reference. And when the test is over, you get half an hour to turn it into a PDF while you're working and send it to me and upload it into Canvas. And trust me, anybody who's had me before, you get a lot more points because partial credit is given by me. Because WebAssign has a horrible thing. It's right or it's wrong. So if it's not right, you get 0 out of 20. But if I see you're working and I find out that you did almost all of it correct, but 2x turned into, I don't know, x squared or something, right? Just a little hiccup. You'll get 90% of the points, right? And so I can't tell that unless I see you're working. So you'll take your working and you will upload it as a PDF. And nearer the time, I'll take you through that process. But I've got a video and some things that'll help you. And the final's kind of a big version of the same idea. Right. Same process. So that'll only happen twice. Does that answer your question?
Yes, thank you.
Okay. Any other questions before we actually get started on our first topic? Okay, sounds like a plan.
Yeah, I was curious, are we going to be like in this type of a class setting too? Like if we had a question, like maybe the wording was confusing to us, like middle of the test, could we ask you? Or
Sure. There's a Zoom meeting going on during the test. That's why I need you all be on video so that I can make sure that, you know, you don't have your brother beside you, you know, doing it for you. Right. So, yeah, and you can ask questions like question 4 doesn't make sense, or what, you know, because it happens sometimes that the way they phrase it is a bit weird, and I can answer that. Right, so let's get started on our first topic. Imagine that someone gave you a job to do, and the job that they gave you was to find the area under the curve from x equals 1, I know this isn't to scale, to x equals 5. And they wanted to know what we call the area under a curve. So it's the area between the x-axis and the curve. So I want to find that area. And I want to try and get the best answer I can. And you might say, well, how do they actually do that? Well, one of the strategies, the one we're going to deal, involves us going, okay, there's 2, there's 3, there's 4, there's 5, is that you take the shape and you break it into 1, 2, 3, 4. Do you see how there's 4 strips there? And I can't tell you what the area of any strip is, but what I can do, however, is I can guesstimate it by doing rectangles. And imagine this is the same curve. There's 1, there's 5, there's 2, 3, 4. So you take this first strip and you can use either the left-hand side, which is this side, or the right-hand side, which is this one, to make a rectangle. And I'm going to take the left-hand side. So there will be my first rectangle. And then I'll take the second strip, I'll take the left-hand side, and there's the rectangle. And then the last one is there. Now I can find areas of rectangles, aren't they just width times height? And I could find the area of 4 rectangles, right? And add them all up. And that would be my estimate for the area under this curve. Would you agree that this estimate is an underestimate? In other words, it's smaller than the real answer. Aren't these red rectangles less than the whole shape would have been? Now, if I go back to the original question, right, this curve y equals x squared again, and there's my same 4 strips, and I have the same choice. I can use the left or the right, but this time I'm going to use the right-hand side. And when I use the right-hand side, I get those guys. And those guys, those 4 rectangles, won't they also be an estimate for the area under this curve? Now, the difference is, aren't these bigger than the real area? So we would say that would be an overestimate. So let me get you some terminology. When you take a shape and you break it into 4 equal strips, as we did here, and you use the left-hand side to get the height, that is called L4. And when you do 4 strips, but you use the right-hand side, right, the right-hand side one, not the 4, but the 5, we call that R5. Now, I can find the area for that, and I will in a few moments, and I can find the area for this, and we'll do that in a few moments, right? And I can say that this answer is an underestimate and this is an overestimate. And so won't I be able to say that the real answer is somewhere between those 2 numbers? And so although I don't know the exact area under that curve, don't I at least know it's between this number and that other number? And that's something. So let's work on the process of finding these rectangles. Well, introduce more notation. The width of a rectangle is going to be called delta x. And I'm going to take the information that is in this graph, and I am going to write down the x coordinate, which is 1, 2, 3, 4, and 5. And the y coordinate, which is, well, when x is 1, I'll make this red. The y coordinate is 1, 4, 9, 16, 25. Okay, in this particular question, I've made delta x very simple. Isn't delta x 1 unit wide? Right, from there to there, isn't that 1 unit wide? If we then look at this set of rectangles, the guy that's called L4, it's going to be made up of the width times the height, width times the height, width times the height, width times the height. So it's going to be something, add something, add something, add something, right? These x coordinates, right, the 1, 2, 3, 4, 5, they have special names. This guy's called x0, oops. This guy's called x1, this guy's called x2, this guy's called x3, and this guy's called x4. So the first one, the start value, is called x0, and the last guy called x4. Now, if I want to find, using this information, that rectangle, it's going to be delta x times the value of the function x0, delta x, the value of the function x1, delta x, the value of the function x2, and finally delta x, the value of the function x3. That's basically width and height of the first guy, second guy, third guy, fourth guy. And then we do this little simplification. Don't all of them use the same value delta x? And isn't this a bit like a common factor? So if I can evaluate this, that's the same thing as getting these 4 rectangles. So here it goes. Delta x is 1 times that guy, that guy, that guy, and lastly that guy. And you put them together and you get 1 times 30. You get 30. So the area of these 4 rectangles is 30. Now, I guess you could have done it without all those notation, but this notation is important because what this allows us to do is to generalize the process. Because maybe I don't want to do 4 strips. Suppose I wanted a more accurate answer. What's the only thing I really could do to get a better estimate? Right now I'm using 4 strips, but if I wanted a better estimate, what could I do?
Use more strips?
Yeah. Now, if I wanted to do 40, can you imagine it would be a little bit messy to write, but I could actually use this process, couldn't you, and just generate a longer table and add up all those values. And delta x, of course, would change value, and we'll talk about that later. Now, if you want to do right 4, it's going to look very similar, but not quite the same. In this case, we used x0, x1, x2, and x3 to get the heights. In this one, we use x1, x2, x3, and finally x4. So it's delta x times the value of the function at 1, and then delta x, the value of the function at 2, and delta x, the value of the function at 3, and finally delta x, the value of the function at 4. Now what does that get us? It gets us, well, oops, almost forgot. You can take out the delta x and now we can do 1 times that guy, that guy, that guy, and that guy. So that's going to be 4 add 9 add 16 add 25. And you put this package together, you get 20, 45, you get 54. So I can tell you that the area under this curve is somewhere between 54 and 30. Not great, right? But at least I know something, right? Now, if I did 8 strips, can you imagine that if I did 8 strips, it might be, and I'm just making this up, but couldn't it be between 37 and 42? And if I did, pretending I did, 1,000,000 strips. Now, nobody would ever think of doing 1,000,000 strips by hand. Wouldn't that go into some computer software? Right, it would do it for us. But if I did 1,000,000, can you imagine that what would happen is
I can't see what you're writing anymore.
couldn't it end up that the 2 different answers were so close to each other that they're both 39 for all intents and purposes, right? You know, 38.200 9s and a 7 and, you know, something like that, but so close to 39. So in a way, if we could increase the number of strips to be infinite, right? Make n become infinite. We actually have a technique that would allow us, if we can figure a way to do it, to get the exact area under a curve. We only do 4 or 5 or 6 by hand just to get a swing for it. But what really happens in a more practical case is that wouldn't you just go to your computer software and say, here is this function, I'd like to know what the area between 1 and 5 is, and oh, do 1,000,000 strips. That should keep you busy for about 0.1 of a second. And then boom, out pops the answer. Now, if you're into programming, can you imagine that it wouldn't be too difficult with a little bit extra knowledge to write a program that could do this? That could calculate the area under a curve for as many strips as possible. So that's the gist of what the first section is about, or at least half of what it's about. So let me show you another question. In this second question, you're not given a function. All you're given is a table of values. And at time 0, at time 0.5, at the 1 second mark, at the 1.5, and let's say at the 2 second mark. And at these given times, the velocities were those numbers. Now, hopefully some of you have done physics. If you take time against velocity, what is the area underneath a velocity time curve? What do you calculate when you do the area under a velocity time? None of you done it? You calculate the distance. So the area under a velocity time curve, and this table is basically the numbers that you're going to use, will give you an estimate for the distance. So let's have a look at this guy. Can you imagine going from one value to the next along the T's? What is delta T? How wide will each strip be using the top row to figure it out?
0.5.
Agreed. Now, if you look at this, there's 1, 2, 3, 4, 5 numbers, but essentially that only gives you 4 strips. Can you imagine 5 points gives you 4 strips? If I plotted them, it might look something like this. At time 0, you get 4. And then at the half second mark, you get 6. And at the 1 second mark, you get 10. And at the 1.5 second mark, you get 13. And at the 2 second mark, you get 15. You can imagine these are the dots. They look something like that. But doesn't 5 dots only give you 4 strips? So I'm going to use the trick that we used before of rectangles. And we are going to find L4 and R4. It's going to be 0.5 times. If you want to find L4, don't you just use these 4 guys? The 4 on the left. So it's going to be 4 odd 6 odd 10 odd 13. And if you want to find R4, it's delta X, 0.5, times the 4 on the right, which is 6 odd 10 odd 13 odd 15. And I should be able to do it in my head, actually. 10, 23, half of that guy, 11.5. $16, 29, 39, 44.
Wouldn't that be
Half. Oops,
33.3 at the top?
This one here.
Isn't L4B? Yeah.
Oh,
And then
thank you.
Yeah.
Thank you. Can't count, as you probably already have realized. That would be 16.5. Write it again. doing it in my head and doing it far too quick. Does the R4 look okay? Was that up right? 18, 28, 18, 38. Yeah. So what can I tell you from this table? Well, my estimate for the distance traveled by this moving object in its first 2 seconds is somewhere between 16.5 and 22. So in WebAssign, you are given 2 boxes, and one of them is called the smaller value, and I think the other is called the larger value. And you pretty much put in 16.5 here and 22. So although I know very little information, I just have snapshots of what the velocity of this moving object is at only these times. I can tell that somewhere between 16.5 and 22 meters is the total distance traveled in those 2 seconds. Now, do you notice that this is an increasing list of numbers? Doesn't that make this function an increasing function? And if you are an increasing function, won't the left and the right be under and over estimates? And if you're a decreasing function, won't the left and right be under and over estimates as well? That's why we can say that the right answer is between these two. One of them is overestimate, the big guy, and one of them is an underestimate. Okay, any questions about how we can find estimates using these tables? Do you want to see another one that is boring as heck, but are you good with one, or do you want to see a second one? Your choice, come on.
I think I'm good.
Yeah, I'm
Good.
pretty confident with those.
Right. They take forever and a bloody day to do. And do you notice that I would have got 0 marks in WebAssign? Well, half marks, because one of them was right. Because all I simply did is add up something carelessly. So be careful, right? And you'll get through it. Well, there is another version of find the distance traveled, find the area under a curve. So let me show you how WebAssign asks those questions. First the table, which we've seen, but then the graphing version. And the graphing version is a real pain in the butt. So here is from launch to separation. And what you have here are some times, and what you have here is some velocities. And what you're being asked here is to find the total distance traveled during this time period. Now, have you noticed that these intervals are not equal? So you're not going to be able to do my shortcut of delta t or delta x. What you're physically going to have to do is this. The first rectangle goes from 0 to 10. Won't that be 10 units wide? Right? 0 to 10. And since they want an upper estimate, won't you pick the 180 as the height? So can you imagine that your first rectangle is just going to be 10 times 180? Now, what's your next rectangle going to look like? Well, 10 to 15. Isn't the width now only going to be 5? And which one of these two numbers will we use for that magic height of the rectangle?
319.
Right? So do you see it's not going to be a single delta x and then you can just add them up? Aren't you basically going to do, what is that, 6 or 7? I can't think. 1, 2, 3, 4, 5, 6, 7, 8. 7 different rectangles, right? Whatever the time difference is times the height. Whatever the next time difference is times its height. So basically a whole load of 2 things multiplied, all added up, right? 7 of them in particular. For instance, won't the last one be 63 times 4,052? And who knows, God, there are, for me, at least 20 different places for me to be careless and screw this up. It's not a difficult process, isn't it? Just be careful. Now, the brave amongst you could probably just grab your calculator and do that on the fly. This times this, add. This times this, add. This times this, add. Me personally, because I screw up when I do that, I write down each one separately, add them, multiply them together separately, and then add the damn thing up. Because that, for me, is the only way that I can be sure that I reduce my chances of making a mistake. And now let's look at the other kind of question. We want to find L6 and R6, but there isn't a function, right? It doesn't say y equals x squared. And there isn't a table where I can get my numbers, which means we're going to have to do the table by using that diagram. So let's see what the first clue is. It starts at 0, which is here, and it finishes at 48. Okay, I can handle that. So I'm writing this down, even though you can't see me writing it down, I'm doing so. And they want us to find left endpoints, L6. So I'm going to go back to my whiteboard and show you my start to this. If you start at 0 and you finish at 48 and you want 1, 2, 3, 4, 5, 6 strips, don't we need to find delta x? Here is the formula for getting delta x. B take away A over N. B is the end. A is the start. And N is how many strips you want. So in this case, 48 take away 0 divided by 6, which comes out as 8. So I will now construct the beginnings of my table. Zero, 8, 16, 24, 32, 40, and 48. Are you comfortable about how I created the x coordinates of my table and why I got what I got, right? Now I need to get the y values, because once I've got that table, then I can find L6, right? So now the awkward part. If this had been a function like x squared, wouldn't I just do 8 squared, 16 squared, 48 squared on my calculator and I'd get the exact answers, right? Not so lucky here. I'm going to make this a little bit bigger if I can. Can I do that easily? Right, that's as big as I can make it. If I look at the vertical scale, would you agree that one box is worth 4? So when I look at what is x equals 0, that one's not too bad. Would you agree it's 36? I don't think we'd argue about it. Right, it's one box above 32, one box is worth 4, 32 add 4, 36. We're cool with that one. Okay, the next guy is 8. 4, 8. 8 is here. If you go up here to there, don't we have to guesstimate what that y value is? Now, don't make your life difficult. Don't try and do one decimal place. Would you agree in the scale that we've got here? Nobody's going to be that good. But hopefully to the nearest whole number. And I'm going to say that that guy is just a little bit shy of 36, and I'm picking 35. but some of you might think it's 34. I think I'm confident it's 35, but can you see that if you're doing this question, it might sometimes be, is it 4 or is it 5? It's 5. And do you know what Murphy's law is going to be? You'll pick 4 and WebAssign thinks it's 5. But if you pick 5, won't WebAssign think it's 4? And you're not going to win that battle. So go with your gut and just stick to the guns. And then when you get your answer, if you end up being a tiny bit out, you'll shoot me an email and say, look, I got 44.5 at the end. They got 46. You know, hey, come on. I'm doing it right. I'm just, it's hard to read things off graphs. And I'll fix that, right? I'll give you the points. Okay, the next guy is 16. So here we go. Any volunteers for what the height would be at 16?
33.
Yeah, I would probably say 33. The next one here is 24. 24 is, darn it, that's 28, so one above it. I'm going to call it 29. 32, that's the only one I don't think I need to argue about. Would you agree that's bang on a line, so it should be an exact number? 16, 24, that makes that guy. If we go to 40, which is here, oh, perfect answer again, 16. I'm not going to argue about that one. And the last one, oh, another perfect answer. So, about half of them we could be pretty sure about because they're exactly on the line. And the other half was, hopefully we guessed correctly. So once you have created this table, we can then move on to the next phase and get L6. Won't L6 be delta X times, if you want L6, don't you use the left 6? Don't you use these guys for your height? So it's going to be delta X times all of these guys added together. But stopping here, right? And delta X is 8. And that's 40, 69, 99, 102, 172, 173. And then doing 8 times 173. And the answer I get here is 1384. So hopefully I did that right. Suppose I wanted to do R6. Wouldn't it still be delta X? What's the only difference? What numbers will I use from my table to get R6?
The right 6.
Yeah. So basically, those 6. So if you've got this table, shouldn't you be able to get R6 and L6? In a different table, wouldn't you be able to get R5 and L5 or R10 and L10, right? Because the same table contains all the numbers that you need. You just need to remember when it's a left, you use the left-hand side and basically ignore the last number. And the other guy, don't you use all the end numbers and ignore the first number. Are we cool with that? Just out of curiosity, has anybody done the second one for me? It starts at 35.
I was in the process of adding it.
Okay, I'll take your answer. I'll just put ... there.
I had 141.
I got 145. No, I'm right.
I think I had a
20.
typo.
You agree on 145? No? Okay, let's do it. 5, 8, 17, 21. Yep, you're right. I'm wrong. It ends in a 1. And so we have 8 times 141, and that is 1120. Oops, 1128. Now I'll return back to that picture, because there's just something we should be able to judge. Looking at that shape then, isn't it a decreasing function? So not only can I tell you that my two estimates are 1384 and 1128, can't I say that 1128 is the underestimate and 1384 is the overestimate? So the true answer is somewhere between those two numbers. Now, if you're given a picture like that, couldn't I do 16 strips? Right, take me twice as long, but couldn't you do 16 strips? It becomes a bit unpractical after that, right? I wouldn't want to do 120 strips or something ridiculous. I don't even think you could do it physically, do it. But as long as you're not overdoing the number of strips, can't you get a pretty crude estimate of the area under the curve, which very often represents distance traveled? Are we cool with that guy? So it's just an extra bit of work. You now have to not just use the table, right, with all the numbers in it. You have to create the table first, and then you can use it with all the numbers in it. So that gets us to this question. Isn't that back to here's a table, get an upper and lower estimate? We've covered that. Isn't this another graph one again? So we can do that. Here's yet another graph one. What's different about this one? Oh, 5 rectangles, lower estimate. Okay, can you imagine 1, 2, 3, 4, 5? The rectangles aren't too difficult to judge, right? Can you imagine? There's my first rectangle, there's my second. If I wanted to do a lower estimate, wouldn't I be using R5, the right-hand side? Right. Take this strip here, the second one. I could use that height, or I could use this side. If I use the right-hand side, won't I make a rectangle that's smaller than the area and underestimate? A lower estimate, as they call it. Now, what would my picture look like? Well, wouldn't it be that picture? So you just put a little dot on it and you got it. Now, if you wanted to do an upper estimate, as they call it, right, I'd call it an overestimate. Wouldn't your picture be that one? And upper estimate and lower estimates, numerically, you put them in here. Now, our next variation on a theme is I'm going to do a version of question 7. I don't know what that's about. Okay. You can't see this right now, but that's fine. So we are going to take a function, in this case 1 plus 2x squared. That's my version of the question. We're going to use it from -1 to 1, and we're going to do 4 strips. And we are going to get an estimate for the answer, and it's going to be an upper and a lower estimate kind of thing, right? So here it goes. If you set up your table with your X and Y values, and you're going to do 4 strips, and you're going to start at -1, which is A. Let's find out what delta x is. B take away A over N. 1 take away -1 divided by 4 strips, and I believe you get a half. And I'm going to call that -0.5, 0, +0.5, and 1.0. Are you all happy about where the x values came from? Start at -1 and keep adding a half, right? 0.5 until you get to the end. Now, if you wanted 8 strips, wouldn't you just do 1 take away -1 divided by 8, and it'd be going up in 0.25s, right? So you'd go -1, -0.75. Now, we need to find these numbers, don't we? But we've actually got a lot of help. Now, I could simply just plug in -1, get the answer, plug in -0.5, get the answer, and it wouldn't take me that long. But let me show you another way that we can do that. So I'm going to use my little TI-84 emulator. And I'll show you a little trick that some of you might want to use. It's up to you. Go to your calculator, type in y equals, and put whatever the function happens to be. In this case, 1 plus 2x squared. Right, that's that bit done. Then go second table setup. And where it says table start, put in the x value where it began. So in this case, -1. And where it says delta table, put in our delta x. Now what that has now done is essentially it's done all the work for us. Because now I just need to go to this guy here called table. So blue button here. And there's all the numbers I want. The guy is 3, 1.5, 1, 1.5, 3. And that's it. Yeah, that's it. And now I'm going to cut a lot of corners here. If you've got a table like this, are you comfortable that you could find L4 and R4 the usual way? Right, won't L4 be using those guys and R4 using those guys? Oh, and make sure that you use the delta X guy, right? Make sure that it's 0.5 that you use, right? Because sometimes people forget, they just add these numbers and forget that there's a width, a delta X going on. Actually, these numbers here are very symmetrical, so it wouldn't surprise me in my question if both answers end up being the same answer. But that's very rare. In the question that they've gave you in the homework, I'm sure that one of the answers is bigger than the other. And that's why it's called an upper and a lower sum. Now, suppose they gave you a function, which is basically what's happening in question 8. And the function is 4 square root of x. And you're going to do it from x equals 0 to x equals 4. And you're being asked to find R4. I'd set up my table. Kind of all begins at the setting up the table. I know the first value is 0. I know the last value is going to be 4. I know how to calculate delta x. It's a b take away n over n. Oh, that's too easy. Isn't it 1? So it just goes 0, 1, 2, 3, 4. And for the f of x, can't you just plug in 0, 1, 2, 3, and 4 and get your answers? I'll just dot this. Once you've done that, won't you use these 4 guys to get R4? And these 4 answers to get L4? We're just repeating ourselves now. If you can create a table, you can create, you've got everything that you need to find R4, L4, R8, L8, whatever they ask. We feel good? Right. I'm not going to do this question, but I'm going to pretend that it's a question and we'll set it up. You're being asked to find L10 of this function between 0 and 5. First thing you would do is calculate delta x. That would allow us to set up our table. Then couldn't I use the calculator to find all these guys? And since I want L10, won't we use the left 10? And if the question was R10, won't you use those guys? Bearing in mind, don't forget that delta x is 0.5, right? It's a half. So if I gave you a function and a question like that, do you feel comfortable that you know how to go about getting the answer?
Yes.
Right. Not very interesting, is it, to be honest? Just, well, you know, just because it's not interesting to me doesn't mean it's not interesting to someone else. Okay. Well, that means that we can pause on that particular piece of the work and move on to a new piece of work, still on that section, but we're going to look at a thing called sigma notation. Right, so here is a very big addition. 1 cubed plus 2 cubed plus 3 cubed all the way to 100 cubed. Massively big calculation. No, you're not going to be asked to do it. That's not what this is about. But mathematically, we do not like things to be clunky. We try and condense that same information into something much more concise, but has exactly the same meaning, right? So the notation that we use when you want to add lots of things together is called sigma notation. That funny letter there is actually the Greek letter sigma. To be more precise, it's the capital sigma. The reason for that is, isn't there in statistics a little guy that looks like that? It's also called sigma, but he's lowercase sigma, right? It's a bit like, you know, capital A and little a, right? They don't look the same, but they're both A. So this is capital sigma, we just call it sigma. And then you put in a variable like k equals 1 to 100. And then you put k cubed there. And this represents the same thing as that. It basically says add together using k equals 1 finishing at k equals 100, the k cubes. Right, let's turn that on its head. I'll just make it 2k, right? What would that look like if we wrote it out with lots of pluses? Well, k equals 1, you get 2 times 1. Plug in 2, plug in 3, and finish with 2 times 50, which is 100. Aren't you basically adding the first 50 even numbers up? So doesn't this notation take something that's quite clunky and condenses it into a very nice little package? So what are the kind of questions that you're going to get? You're going to get questions like, take this guy and turn them into that. Or you're going to get a question that looks like this. Where they actually want you to find out what that's equal to. So if you plug in 1, won't you get 3.2? If you plug in 2, don't you get 3.4? If you plug in 3, you get 3.6. Then the next one, 3.8. And won't the last one give you 4? And then simply add the whole lot up and get whatever the answer is. It's not difficult to do, it just takes time. We call on sigma notation and how it can be used to take lots of things being added and convert them into a very precise
If
piece of
k was
notation.
equal to 2, would you go up by 2 every time?
No, actually, but it's a good question. Suppose I write down the exact same question, but with one alteration. When k equals 2, so you start with k equals 2, 3.4, 3.6, 3.8, and you finish when it's 5, which is 4. So do you notice that the difference is that you only add up 4 numbers?
Okay.
So it allows you to add up a whole load of things. I think it's more natural that you would start at k equals 1, but I guess there might be some situations where you don't want to add the first number, right? You don't like it for some reason, and you just want to add up everybody else apart from him, in which case this can be adapted quite easily to do that. Now, let me show you sigma notation being used to make a formula that I've already written easier and simpler to write. Can you remember I did something like L6? And it was delta x f, oh, let's change that. Let's do R6. So it'd be 1, 2, 3, 4, 5, 6. That's a beast of a thing to write down, isn't it? However, how about k equals 1 to 6 of delta x s of f little k? Mathematically, isn't that the same thing as that? Isn't it? Plug in 1, you get this guy, plug in 2. I mean, if you wanted to, I guess I could have written it down like that. Do you see it a little bit more now? What does that allow me to do? Well, guess what? Haven't I just written a formula down for R of 600 that doesn't require a whole load of writing with dots everywhere. Kind of cool. It allows us to, relatively speaking, combine things into quite small things. Any questions about Sigma notation? Are we good? Right. Well, I'm going to give you now the general technique for finding the exact value under a curve. And this is, I'm warning you up front, this is going to look weird because it is. And it's going to be, there's no short way of saying it. It's just going to be messy and you're just going to have to try and fight your way through it. So if it doesn't make sense the first time, you might want to go back, look at this video and just play this piece over again. Maybe the second or the third time it'll finally click. So we're going to take a function, a general function. And this function is going to be called y equals f of x. And because it's a general function, it's going to start at a and it's going to finish at x equals b. And we are going to split this into n strips. And we are going to write down a formula for calculating what Rn would be, where n could be 200 strips or 4,000 strips, right? Just a general n, no numbers anywhere. That's what's going to make this awkward. Okay. So if you were going to take this information and imagine that it was numbers, wouldn't delta x be b minus a over n? Agreed? Now, I'm trying to set up my table of what it would look like. Well, the only easy one is a, which, by the way, we call x naught, right? What would the next x coordinate be? Well, if you make this distance delta x, won't this guy be a plus delta x? Would you agree the next x coordinate in this very general process is a plus delta x? And won't we call this guy x1? Now, what would the next guy be? The guy that we would call x2. What would he be?
A plus 2 times delta. Oh, wait.
Yeah, you're right. A plus 2 times delta x. If you think about it, to get to this point, don't you start with a and add 2 delta x's to it? Now, you can't do this forever because it's unknown, but won't you go dot, 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 right? And then won't you finish at the last guy? And the last guy would be called xn. And won't the last guy, if you do it correctly, won't the last guy be b? And then you have the value of the function, right? In this case, f of a, then f of a plus delta x, and then f of a plus 2 delta x, and so on, right? And then at the end, f of b. So far, so good? Now, let's do Rn. If you're doing Rn, don't you basically just ignore that guy? And isn't it these guys that you use. You agreed? So what would you get? You would get delta x and these guys added. So it would be f of a plus that guy plus a of that guy all the way to the end. I'm just going to rewrite this slightly differently. Since xn is this guy and x2 is this and x1 is that, and these two equivalent, they're just different ways of saying them. Which means that Rn in sigma notation can be written as k equals 1 to n delta x f of x k. So I've taken this ugly thing and rewritten it as this guy. So far, so good? Agreed? Now, you might think, hey, can we finish now, please? No. Delta x is going to be replaced by that guy. The guy called xk is going to be replaced by one of these fellas. And that's where it gets a little bit tricky. Can you imagine somewhere randomly at position k? What would that guy look like? Well, when it was x1, isn't it a plus 1 delta x? When it was x2, isn't it a plus 2 delta x? Can you imagine what xk would be? A plus k delta x's. Are you happy about a plus k delta x and where that came from? So that's going to be a plus k delta x. And then you might say, please, can we be finished? And the answer is not quite, but we're darn close. What can we replace delta x by? Well, we can change it into. And it is actually on this page. What can delta x be replaced by?
E minus A over N.
Yeah,
Minus A over N.
agreed. Would you agree that is the ugliest looking thing you've probably seen for ages?
Yes.
But that is the general version of every right n Rn that you could ever do. See, if I start telling you stuff, A is 10, B is 40, N is 5,000, f of x is x cubed, couldn't you plug it all into this and you'd eventually get an answer? Theoretically, at least. So the last step is this. The true area, the exact area, is just the limit as n tends to infinity of that guy. Would that make sense? If you made an infinite number of strips, you could get to the point where the answer to the area from the rectangles is the same thing as the exact area. That makes sense. 2 million strips, you're darn close. 2 billion strips, nobody could tell the difference. And that's essentially what this is saying. The area under a curve is the limit as n tends to infinity of Rn, where Rn is this ugly mess. Now I'm going to write that guy down again, because it's one of those things that's very hard to memorize. And we are going to use it to answer a couple of homework questions. Suppose I gave you the function tan x, and I told you that it was going to go from x equals 0 to 2. How could you find the exact area under this curve from 0 to 2? Well, Rn is sigma k equals 1 to n. Now, won't delta x be 2 take away 0 over n? Won't delta x just turn into 2 over n? The function is tan a, which is 0, plus k times delta x, which is 2 over n, sigma k equals 1 to n, 2 over n, the tangent of 2k over n. And so A, the exact area, is going to be the limit as n tends to infinity of k equals 1 to n of this fella. That's the weird guy I was talking about. This one is a version of question 14. The function is x squared plus that guy. X is between 2 and 4. And we are already given this bit. Oh, don't know why they chose to do I equals. Can't you do k equals 1 to n, I equals 1 to n, any letter you like, but I is what they've got. So here goes. Don't I need to find b minus a over n? Right? Delta x. 4 take away 2 over n. That's delta x. This horrible function. And we're ready. Well, this horrible function has to be evaluated at a plus k delta x at 2 plus that guy. So instead of x squared, it's 2 plus 2 over k squared plus the square root of 1 plus 2 times that fella, which is 2 plus 2 over k over n. And I've just put k's in, and I screwed up there because what letter should I have used because of this thing? I should have used i's. You know, they want to change the letter halfway through the work. That's great. By the way, the earlier sigmas used k's, and now for some reason they just decided halfway through to change them into i's. Who knows, they might have a p equals 1 to n, you know, later on. Here's a different version of that question turned on its head. This is homework question 15. That's the guy. One of these is the right function. And one of these matches the right interval. All the clues are there. It's just a little bit harder. Okay. Would you agree that that guy there, the tangent, tells me that the function is going to be tan x? That means I'm not going to even look at that guy or that guy because they don't have tan x, they have x. That's good. Now, would you agree that this guy here represents delta x? And this guy here represents a plus delta xi. I don't see any a here. I don't see 1 plus something. So doesn't that tell me that I should be starting with a 0? So that means it can either be this guy or this guy. Not that one, right? Now, when you plug in the last I, right, when you plug in n and you put it here, don't you end up with pi over 3? And if you plug in pi over 3, do you see that the guy, whoops, the guy that you get is that one. So when you take all the pieces, all the clues that are there, doesn't that end up being the only one that fits all the clues? That's a darn sneaky question. That guy there is something we haven't done yet, so I am going to make this the last question for today. We are going to find the exact value for y equals x cubed. X going from 0 to 1. Okay, here goes. A, B. Delta x is b take away a over n. Delta x is 1 over n. Let's go. Rn is going to be sigma.
Can't see if you're writing anything.
Oh, thank you. I got caught up in the moment and forgot where I was on the screen. Right. So start this off again. Y equals x cubed. So this is essentially question 16. So we're kind of doing this together. Y equals x cubed from 0 to 1. I just calculated that delta x is this, and I'm now doing the Rn. Rn is delta x, right? The value of the function at a, oh darn it, it's I equals 1 to n again, but I can live with that. A plus I delta x. Okay, so sigma I equals 1 to n, 1 over n. The value of the function at 0 plus I times this guy, which ends up being that fella, which is I equals 1 to n, 1 over n, the value of the function at I over n, is I equals 1 to n, 1 over n. If you evaluate I over n and you cube it, don't you get I cubed over n cubed? Which means that we get sigma I equals 1 to n of I cubed over n to the 4. Now what you can't see, but I can see in front of me, is that guy there, right, this I cubed bit, can be replaced. The entire whole lot, that guy there, can be replaced by an n n plus 1 squared. No, sorry, n plus 1 all over 2 squared. Let me write that again. n plus 1 all over 2 squared divided by n to the 4. Whoa, that's going to look fun. If you take this mess and you tidy up a little bit, you get that. And you bring in the n to the 4, you get that. I'm going to cancel some n squareds. I'm then going to multiply out the top. I'm then going to separate them into 3 distinct pieces. And this guy cancels and gets me a quarter. This guy cancels and gets me that. And this guy gets me that. So what I have found is that Rn is that guy. Over here then, the limit as n tends to infinity of Rn ends up being that, because Rn ends up being this. Oh, and that's easy. If you make n infinite, won't that be 0 and that will be 0 and you're left with a quarter? So the exact area of x cubed between 0 and 1, right? The exact area under the curve is 1/4. So it's not even an estimate. You'll be glad to know that that is not going to be the way that we typically find areas under curves. We are going to show you a really dead, sneaky, clever way of getting that. But that's something that still has to come. Are you okay so far with what we've done? This last one, it won't surprise me if you have to go and look at it a couple of times just to figure out all the different steps that took me to that point. But that is actually the last question from that particular group. So